Thanks, Amy. This is joint work with my advisor, Michael Poza. So all the biological and mechanical systems that we've been talking about over the last few days, the primary physical phenomenon that drives their motion is frictional contact with the ground. And often a large portion of the aggregate effect of this phenomenon happens right at the moment of footfall in an impact event. And if we're going to be encoding notions of impact into the models that we're using to make our controllers, we had better hope that the impact behaviors in the models match reality. But unfortunately, even the most simple first principles-driven models of impact are riddled with mathematical inconsistencies. One of the easiest ways to excite these inconsistencies is non-uniqueness through simultaneous impact. So consider one of the most simple models of walking a rimless wheel. So it's just a center mass with a bunch of spokes connected to it. We're going to take this object and we're going to throw it straight down into the ground and ask, what would happen if we had an inelastic impact with the ground? One reasonable first principles approach is to say there's some sort of symmetry here. There's going to be an even effect at the left and right foot, and we would expect the object to come to rest. Just as easily, we could say that we think that the friction with the ground is enough to prevent slipping, and we could first resolve an inelastic impact at the left foot, and we would start rotating about the left foot. But then the right foot would be sinking into the ground. We need another inelastic impact, and the final result would be the object would start spinning off to the right. We could just as easily reverse this process and get an exact mirror image of this result. So now what we have is three categorically different predictions for what happens in this scenario, and it's not immediately clear which is the most reasonable for a representative physical system, nor is it clear whether or not intermediate results between these would also be reasonable. These inconsistencies aren't limited to these simple models. David Remy a couple of years ago at Dynamic Walking saw some similar behaviors in a much more complex model. And non-uniqueness in models is often paired with extreme sensitivity in real systems. A classic example being a billiard break, where it's nearly impossible to predict post-impact states. So if we'd really like to make reliable control for walking and running systems, then we need to be able to handle this non-uniqueness. And if we would like to do so rigorously, it would be good to have a model that is capable of producing all of these non-unique behaviors. So we contribute exactly one such model for simultaneous inelastic impacts. We prove that there is existence of solutions to our model under minor conditions. We want to point out that we're solving a fundamentally different problem than simulation methods, which focus on predicting a single plausible post-impact state, whereas we are capable of capturing a very large set. Before we get into the details of our particular model, we're going to review the theoretical basis, which is E.J. Ralph's original 1891 model of single frictional impacts. It obeys some notion of Newton's second law, where V plus and V minus are the post and pre-impact velocities, and capital lambda is the net impulse at the contact. Ralph took a differential perspective on calculating the post-impact velocity and the impact impulse simultaneously, in which the total normal impulse is continuously increased with some constant slope, and the frictional impulse is incremented via Coulomb friction rules. So what does this look like on a simple system? So basically the simplest impact we could have is a square block just hitting the ground. We'll model this as happening at a single point. And we have a pre-impact velocity shown here in yellow. If we want to think about a differential process of updating this like Ralph, we might think of taking a picture of velocity space and painting on it arrows that represent how the velocity will be changed by our increments in impulse. As we would expect in the bottom left corner, this is where a bunch of velocities that are sinking and moving to the left. We would expect, some upward component due to normal force and some rightward component due to resistive frictional force. So we could follow along this vector field to get Ralph's solution. So here we have our pre-impact velocity, which goes up along this, this field to a post-impact state of just zero velocity. And we can also see some different behaviors in this model as well. So if you come into the ground at a very shallow angle, you might expect that the block is still going to slide after the impact, and Ralph's model is able to predict that as well. Mathematically, if we're talking about capturing the evolution of functions that travel along some vector field, you might think of capturing this as some differential equation, but because there are discontinuities in this vector field, we'll have to use a slightly more complicated object, a differential inclusion. And rather than saying that the derivative of some function has to be equal to one exact particular value, we allow it to lie in some set. So we constructed what we think is the most natural permissive extension of this method, where when we have multiple simultaneous impacts, what we do is we query Ralph's method for valid increments on the velocity due to each individual impact, and then we take some convex combination of those directions. So slope here is slope here you can think of as like taking, so this is all supposed to happen at some instant, but we're still incrementing over some variable. You can think of that as like some very widely different scaled time in which we're viewing this process as incrementation of force over a near instantaneous event.
Force divided by time.
Yes, more or less. So higher slopes correspond to impacts resolving faster, quote unquote, in one contact than another. So we can apply this to our rimless wheel scenario, and here we plotted the evolution of a few solutions to our system. Here we've plotted the velocities projected onto the contact normals. So the bottom left quadrant here corresponds to both feet sinking, and the top right quadrant corresponds to both feet lifting off. And in the blue and the red, we see mirror images which correspond to resolving left foot and right foot and vice versa. And because we're allowing convex combinations of these two effects, we could pick something right in the middle, this yellow dashed line, and then we get exactly the solution of the object coming to rest that we've seen before. But we're not restricting ourselves to an exact balance between these two effects. We allow any relative rate. So instead of just producing these three isolated post-impact behaviors, we predict this entire green section here, which includes all reasonable intermediate values as well. Just like Ralph's method, you can capture this as a differential inclusion, and it's very well behaved, which will enable some theoretical properties that we'll discuss later. So we might ask, is this something that only applies to these pathological instances where you have to have two legs impact the ground at exactly the same time, which is practically impossible to replicate? But there are actually, less antagonistic scenarios in which we think it's important to capture non-uniqueness. So one scenario that isn't quite as much of a corner case is ironically a corner. So what we have here is a yellow object that is scraping along the ground at point A, and then it impacts a wall at point B. So we can apply our method to this system. Here we're plotting the velocities of the blue and the red point on the object in their contact frame. So left and right is sliding left and right. Up and down is lifting off the surface and penetrating the surface. Here we'll do a sequential resolution. So we'll take contact B down here, which is just penetrating and not sliding, and push it all the way up. So we complete this impact here, but that will cause the object to start twisting, and then the point A will start sinking into the ground. So resolve an impulse at point A, and the result is that contact A is basically sticking, and contact B is lifting off of the wall. But our model will allow us to interrupt this process and do something slightly different ordered, where we mostly resolve the impulse at contact B, and then we switch over and push a little bit at A and go back and forth. And we get this very subtly different solution where both contacts are now essentially sliding along their surfaces. It's not immediately clear why you would have non-uniqueness here, but when you forget about all these simplifying rigid body examples and start thinking about solid mechanics, there are shock waves traveling all around in this body, and they're quite sensitive to the initial conditions, and we don't quite know how they're going to evolve. So our model is able to capture that sensitivity with a small degree of non-uniqueness. Beyond exciting all these interesting scenarios, our model is very well behaved and theoretically proven to do so. So it dissipates kinetic energy like most inelastic impact models. There's a homogeneous relationship between pre-impact velocity and post-impact velocity. And critically, we prove that there is a solution to this differential inclusion regardless of what the pre-impact velocity is. But the way in which we are interpreting solutions to this model means that we need something more than just saying that there's a solution to it. Our solutions correspond to evolution of the velocity, and we must say that that velocity reaches some state where we think that that state is a reasonable post-impact velocity. So, penetrating velocities between rigid bodies need to eventually be eliminated. This is something that's so simple in the single contact case that we don't even think about it. So if we travel back to our block hitting a table example, you can see that any velocity with a negative vertical component that would be penetrating into the ground, the corresponding solutions all push it up at some minimum rate. So we're eventually going to eliminate that penetrating velocity quite quickly. However, in multi-contact space, just saying like, oh, all velocities move in one direction isn't quite so clear, especially when you have antagonistic scenarios like this, where you have a movable red object jammed between two blue unmovable surfaces. And the key theoretical result that we've gotten is that this is the only scenario in which our model does not provably converge to a valid post-impact state. So in that sense, it's going to apply to basically every scenario we could want in locomotion, and then some, many scenarios in robotic manipulation as well. So in summary, we've rigorously derived a model of simultaneous inelastic impact. We hope to generalize this to elastic impacts and embed it in the full dynamics of rigid bodies with contact. And most importantly, we've presented this theoretical model. We have a couple computational schemes in the work to compute approximations of the post-impact set given a pre-impact condition. A full version of this paper is going to be available at RSS 2019 in Freiburg, and you can read it online at our website. And finally, we'd like to thank the NSF for supporting this research. Thank you.
Questions?
Sam Burton from UW Seattle. How does it compare to experimental results?
We don't have it yet.
But there's
a
a lot of published results.
Right, yeah, there's a lot of literature on it. I think that's something that's important work for the future. I think something that's important to note with this model is that when you have a single impact, this model only produces a single result. And there are plenty of notions in literature about ambiguities even under single contacts and what model should be using for that. I think you're going to have to add some addition of noise in here to really capture some non-uniqueness in those scenarios. But yeah, it's definitely a line of work we're going to have to commit to in the future. We're going to say that this is going to be representative of physical systems.
I couldn't follow at the beginning where you're doing the differential inclusions. If you assumed frictionless contact, your whole thing gives a different. You also get this family of solutions. So part of the non-uniqueness comes from the friction, and part of it comes from the order, the relative timing of the collision. And both of those are in this model.
Yeah, so you can have frictionless contacts as well in this model. For this really simple example, the vector field would just be arrow center straight up below the horizontal. You still do have non-uniqueness without friction when you do multiple contacts because of allowing these convex combinations.
And you have that in here.
Yeah, it's something the model can capture. I haven't presented any examples in the slides that are frictionless, but we can smoothly include frictionless contacts, even in conjunction with frictional contacts in the space of models that we include properties for.
And then you get unique solution. Are they to follow the complementarity rules in the case? Like if you just take the cantilever that you hit up this hanging
right.
on the wall and you hit
yeah, so you will get in some scenarios, you could have a unique solution from Ralph's method, even just the original one, and a unique solution from a time-stepping method, complementarity method that are distinct from each other.
And this one gives the Ralph.
Yes, this one gives the Ralph answer.
In the frictionless case, this will satisfy complementarity. So it won't
What?
It'll satisfy complementarity.
It will.
In the frictionless case, yeah. So it won't get your rod, the cantilever rod ball.
So it gets that problem wrong.
Yes.
Can you explain that, please? You guys all know what you're talking about.
No, we don't all know what we're talking about, but we can still talk about it. The complementarity thing, I'll just give a short thing, is that when things collide, you assume that either they have an impulse or they separate. But they don't separate. If they separate on their own, you don't have an impulse. So this is there's this assumption that either things are pressing against each other, but when they're separating, they're not pressing against each other. So if you take a computer like this and you put it on a shelf, and then you hit this with a hammer over here, you think, oh, this end pops up, so there's no collision over here. And then the complementarity says, if it goes up on its own, there's no impulse over here. That's the assumption that's made in these complementarity calculations. But if you take a computer like this and put it on a shelf and hit it with a hammer over here and measure the force over here, there actually is an impulse over here. It violates your intuition a little bit, but that's because of all the shock waves and so on that he's talking about. So in the experiment, where you take something that looks like it's pretty rigid and you do the experiment, the complementarity gives the wrong answer. Was that clear for you? Thank you. Well, Chatterjee, Nanda Chatterjee had this great line about this. So collision forces in materials touching each other come from deformations, and that includes collision forces. So he said the concept of rigid body collisions is an oxymoron. So when you try to figure out, what would happen in the rigid limit, that's something you can't even think about. Because to dissect it, you have to think somehow about the process. Is that?
So one more question, if you
In talking about the corner example, you mentioned that sometimes you have to resolve some of the contact and then switch back and forth. Does this ever get into like a Zeno issue where you keep switching, and if not, how do you resolve it?
So because of the structure of this model as a differential inclusion, it can smoothly go through Zeno-like phenomenon. Though, just because it's still like a continuous time model, there aren't necessarily great computational schemes for it yet. And as for what the computational schemes would handle Zeno's paradox, or not Zeno's paradox, but Zeno phenomenon, that's going to depend on what ones we develop.
Do people want to know what they're talking about?
Yeah, so Zeno phenomenon is like you have a ball bouncing on the ground and bounce lower and lower each time, and then eventually the time between the collisions approaches zero. So you have an infinite amount of collisions in a finite amount of time.
And your model might give that.
Yeah, my model might have that behavior in a finite amount of time, but so simulation schemes based off of it are going to have to be able to smooth through that somehow.
So let's thank the speaker.